Welcome back. Thank you for coming back. Let's see. So today I promised to you two things. I promised to show you Volkov proof of periodicity for A tensor A, and I promised to show you some generalizations of all this stuff and some open questions. So I'm a little worried I will not have time for the second part. So I will start with the second part, and then whatever time remains, I will try to show you Volkov's proof in that time. Okay, uh, so far we've been talking about uh, keywords with subadditive labels. But what happens if our labeling is weakly subadditive? Right. So remember, I asked you to classify such keywords, and if you try to do it, you would see that the answer is so-called. Yes, there's some question somebody raised, and
No, I thought it was a question I want to answer. I'm sorry.
oh yeah, you can answer. Yeah. So what's the answer?
Well, I mean, we have to substitute AD parts to AD. Okay, AD parts of which consist of AD Duncan diagrams to parts that consist of affine AD Duncan diagrams, which are basically AD Duncan diagrams with one extra layer, with one extra node, which corresponds to, well, a certain shift in reflection class.
That's right. That's right. So there's the so-called affine AG diagram, right? So you add one more vertex. So if you have type A, you add one guy to make it a circle. If you have type D, you add one guy to kind of make it fork on the other side. And then in type E, there is like, you just need to remember where to add them. And I always forget, I think this is affine E6 maybe, and there is affine E7 and affine E8. So, and you can check that those have weakly subadditive labelings, right? So this one is the easiest. You just put one everywhere. And this is like twice one is one plus one, right? So it's a equality holds. So, and of course, so as I told you, because those don't have strictly subadditive labeling, if you try to run something like our kind of T system on those, they will not be periodic, but the question is, what are they? So let's try it. Let's try. And the simplest one is just this one. This is called Kronecker-Peewer. And think of it as affine A1. Like you have A1 and you add one vertex and you kind of, right? So let's just take this Peewer. It has weakly subadditive labeling 1, 1. And you should really think about it this like twice 1 is greater or equals than 1 plus 1, right? So we sum over the edges, right? So there's two edges coming out from this vertex. So we sum the end, whatever is on the other end for both edges, which means we'll sum this guy twice, which is true. So this is a weakly subadditive labeling. It's an affine Fourier of type A1. So let's see what happens if we try to run our T system here. Does everybody understand what I'm trying to do? And so I'll just try to do the same Zamolodchikov dynamics bipartite T system for this Fourier. And let's just start with numbers 1 and 1. So what happens? So we start with 1, 1. Now, what's the formula here? If this is X and this is Y, the formula looks like this. X times X prime equals Y squared plus 1. Right? So old variable times new variable is product over outgoing arrows plus product over incoming arrows. Yeah. So this is the dynamics. And from this, X prime is just Y squared plus 1 over X. So let's try it. 1 squared plus 1 divided by 1 is 2. 2 squared plus 1 divided by 1, that's 5. 5 squared plus 1 divided by 2, 13. 13 squared plus 1 divided by 5, that's 34. Okay, now the question is, does anybody recognize those numbers?
Fibonacci numbers with some parity.
Yeah, it's every other Fibonacci number, right? So we are skipping, like, there's like, Fibonacci numbers is like 1, 1, 2, 3, 5, 8, 13, right? Each next one is the sum of the two previous ones. But here we kind of take every other one, I guess, etc. So the next one would be, well, whatever, you can find it. So it's a nice exercise to try to prove it. It's like a small Olympiad problem. But of course, if we started not with 1, 1, but with some other numbers, we would get something else. It wouldn't even necessarily be integer, although we could find other numbers which would give us integers. But what's a nice property here? Can we find a nice property which holds? Because periodicity will not hold, right? Those will just keep growing forever. They will forever stay those, keep going, being next Fibonacci numbers. So I want to suggest to you the nice property which holds here. You probably want one more over here. So the next one, does anybody remember the next one? So the next one is 21.
34, 55,
4,
89.
55, 89. So the next one will be, skipping one will be 89. So the next one will be 89, 34. So here's what I claim. If we pull those x's and pull those y's, like this is like x1, x2, x, etc. I claim that the following is true. Xi minus 7xi plus 1 plus xi plus 2 is 0. Okay, so I don't know, let's try it. 1 minus 7 times 2 plus 13 is 0. 2 minus 7 times 13 plus 89 is 0. Does it seem true? It seems true. We can actually do it on the other side. 1 minus 7 times 5 plus 34 is 0. So what is true is that they satisfy a linear recurrence. I think in Ukrainian it would be called возвратні послідовності. I'm not sure, but I think that's how it's called. So this is this sequence. If you just observe what numbers we get at a particular vertex of this quiver, the sequence will satisfy a linear recurrence. In general, it will not be like that. So I will very soon try to convince you that in general, if you just start with some arbitrary bipartite T system like that, those numbers will grow too fast to satisfy linear recurrence. So there is something still special happening. They are not periodic, but they don't grow very fast. They still satisfy linear recurrence. This is a very delicate property. So that's what we will be looking for. Okay, so this will be our analog of periodicity. We will call it Zamolodchikov integrability. That's what Pasha and I called it. So the key property to look at is, again, you just pick one vertex and see what sequence you get there. And you see that satisfies linear recurrence. In this case, we kind of got a coincidence because the linear recurrence for two vertices is actually the same one. But doesn't have to be the same, just separately for each vertex. You look at the sequence and you want to check if it satisfies linear recurrence. Okay. So just to show you how it works, let me convince you that actually it works for this quiver. Okay, I will prove to you that for this quiver, no matter what you start with, no matter what numbers, the sequence will satisfy linear recurrence. It won't be very long. Let's see how the proof works. In fact, there is even something nicer happening here than this recurrence. Let's just treat it as not two separate sequences. Let's treat it as one sequence. 1, 2, 5, 13, 34, etc. I claim that even this sequence satisfies the linear recurrence. This sequence will satisfy recurrence like this: zi minus 3, zi plus 1, plus zi plus 2 equals 0. We can check, right? Basically, this plus this divided by 3 is this. This plus this divided by 3 is this. Like, etc. Can people see this? So, yes? No? Are we okay?
It's okay.
Yeah, so this is a little weird, but it will be easier to prove it in this form. So now, of course, what are those two sequences? Those two sequences are just me picking every other term. Like if I pick those terms, it will be my right side. If I pick those terms, it will be my left side. So here's a small exercise. If you know enough about sequences which satisfy linear recurrence, I will remind you some things. But it's easy to show that if a sequence satisfies linear recurrence, then if you just drop every other term, kind of half of the sequence also satisfies linear recurrence. So of course, it's enough to show that this kind of combined sequence satisfies recurrence, and then it will be a different one, right? You see this coefficient changed. But if this thing satisfies linear recurrence, then each of those separately satisfies linear recurrence. So it's not that hard to convince yourself that that's how things work. So let's prove this. Let's prove that this sequence over here satisfies linear recurrence. And how is this sequence built? It just looks like this. You know, Z1 is X, Z2 is Y, and then, you know, I plus 2 is equal to, let's see, Zi plus 1 squared plus 1 divided by Zi. Something like this, right? So the next term, so you can start writing them out like X, Y squared plus 1 divided by X, then whatever the next guy is supposed to be, etc. Okay. So far, so good. It's actually a nice exercise. I was thinking of assigning it as an exercise, but I thought it was maybe a little too hard to just expect you to do it in a couple of days. So I'll just show you how to do it. Any questions so far? Any questions what I'm trying to do? I just want to give you a feeling what it takes to show something like this. Okay, so I want to show that this sequence will satisfy linear recurrence. And the linear recurrence, now forget the numbers, if we are just doing it for variables. In this case, it will be pretty short. It will be just this length 3 kind of thing. And it will look like this. Zi plus 2 minus a Zi plus 1 plus Zi equals 0. So I claim that there is an a, which depends on those initial conditions, such that this is always true. And this a is called conserved quantity. So let's take a equal to, and here's what it's supposed to be: x squared plus y squared plus 1 divided by xy. Now, I'm not telling you where I got this. For all you know, I just guessed it. Okay, so, and it's kind of a hard problem. If somebody gives you a dynamical system, what are the conserved quantities of this dynamical system? It's not an easy, there is no sort of algorithm to do it. It takes human ingenuity every time to come up with those conserved quantities. But now that I told you that this will be conserved quantity, so lemma. This is a conserved quantity. What does it mean? It means that if I compute it in my original pair, well, I have this formula over there. Now, I claim that I get the same thing if I compute it in any cluster, right? So in any consecutive pair. So let's just check that the next cluster will give us the same value. So proved, right? So does it make sense what I'm trying to do? Instead of x and y, I will now plug in y and whatever this is, and I will check that this didn't change. Okay, so that's my first step. That's what I want to do. So y squared plus 1 divided by x squared plus 1 divided by y times y squared plus 1 divided by x. Okay, I have this computation here, but you can just check that if you simplify this, you will get this again. Okay, so that's it. So this proves that this quantity over here is a conserved quantity of the system. It's a very simple computation. You should do it. It's fun. And now once we know it, we can just check that this holds for one case, and then it will hold for any of them, because all of them looks the same now. All of them will have the same A. So after this, we just need to check that if I want to prove that, now the theorem is that di plus 2 minus a di plus 1 plus di equals 0 for any I. And proof, because it's a conserved quantity, it's enough to check it for just one moment in time. Because for any other moment, it just looks the same because A is, I mean, I don't know how to say it. Like any other moment in time would look the same, except it might have a different A, but it doesn't because A is a conserved quantity. So A would still be the same. Yeah, so, and then you just plug it in. We just do like y squared plus 1 over x minus x squared plus y squared plus 1 over xy times y plus x. And it's almost trivial, I think, to see. Is it almost trivial? Yeah, I think it's almost true. I mean, it's trivial to see that it's equal to 0. And by the way, that's how it will work in general. Whenever we will have the situation where every vertex of our quiver satisfies linear recurrence, the coefficients of those recurrences will be some conserved quantities. And it's a tricky question, what are they and what is this recurrence, how to write it down. But in this case, it's simple, right? In this case, it's just this. Okay, so far so good. So yeah, any questions about this so far? No questions. Okay. So let me remind you vaguely something from the theory of those linear recurrent sequences. If any linear recurrence has, say this linear recurrence has associated polynomial. and I hope it's clear what I mean in general, right? So to any linear recurrence, you can associate polynomial, which will have roots. Will have roots T1, T2, etc., up to the degree of the polynomial. Or maybe let's call them lambda, lambda 1, lambda 2, etc. And then the solution to this linear recurrence will look like zi is equal to some coefficient times lambda 1 to I plus some coefficient lambda 2 to I, etc. It gets a little more tricky if the polynomial has a repeated root, but it doesn't really matter. So for what I'm going to say, so let's just assume it doesn't have repeated roots. That's how solutions look like. That's how Fibonacci sequence. If you ever saw a formula for Fibonacci sequence, it looks like one complex number, golden section time to the power plus whatever conjugate of that to the power. That's where it comes from, right? The roots of the polynomial to the time. So if one of those is the largest, if say this thing has real roots and one of them is the largest, then this will be approximately as big as just some constant times some number to I. Okay, so this says that if our sequence satisfies linear recurrence, then asymptotically it grows approximately exponentially, like exponential of time, right? I is our time, how many times we did our steps, and our variables should be approximately some numbers, the largest root of this polynomial to that time. And we can check that it makes sense, for example. So if you think about it, what was our recursion over here? If we have this quiver, if this is approximately what the variables are, then after I steps, this one is approximately some number times lambda to the I, and this one is approximately some number to lambda to the I plus 1. And we can check that it works out, right? Because look, the old variable times something, the new one, is equal square of this one plus 1. Well, plus 1 is small, but you can see from here that square question mark should be approximately c to the lambda I plus 2, which is what we expect it to be, right? It's the next step. So it should be, by this formula, c to the lambda I plus 2. Okay, so it's what I would call a sanity check, that our solutions to a linear recurrence grow approximately correctly to satisfy recurrence of this quiver. Okay, does it make sense? Any questions? Now imagine that we had a different situation. Imagine that our quiver looked like this. It had 3 edges like this. Well, there's no chance, I claim that there's no chance those sequences could come from linear recurrences now. Because if they come from linear recurrences, we would again have something like c to the lambda to the I and c to the lambda to the I plus 1. But then the recursion would look like c to the lambda to the I times question mark is equal to c to the lambda approximately equal I plus 1 cubed plus 1, which would make question mark approximately c squared lambda to the I 2I plus 2, which is too big. It's not the right, it's not lambda to the I plus 2. Or whatever, to 2I plus 3 or whatever it's supposed to be. Which means, and you can make this rigorous. So this just approximate asymptotics proves that this quiver could never satisfy linear recurrence. If you like, it could never have this property. If you start doing it with this quiver, and we could start doing it like we could just try it with numbers like 1, 1, whatever it will be after that. The numbers will grow too fast. They just grow too fast to be like constant to the time. In fact, they will be probably, yeah, they will grow way too fast for that. So it is some delicate property of a quiver. If you start doing this T system and your numbers grow not too fast, and in fact, they satisfy this delicate property of satisfying some linear recurrence. Okay, any questions about it? So you could ask the following question. You could ask, which, bipartite T systems, right? The same kind we were talking about before. Give sequences satisfying linear recurrence. So this is this question in the spirit of the Zamolodchikov question, right? So again, this one kind of has both directions. So here's one answer. There is a whole classification. So hopefully Sylvester showed you classification of those what we call finite box product finite quivers, right? So this is classification by Stambridge. One of the families in this classification is a tensor products. Remember those tensor products. And those have the properties that they are periodic. And this is type A. I will try to show you today if I have time. So there's tensor product, but there's more. There are other kinds of families. In particular, it was this big conjecture for a while, which was solved by Keller. The tensor product of any two AGE linking diagrams has periodicity property. Well, you could ask, what is the analog of this conjecture in our world, in this new world where instead of periodicity, we look for linear recurrence? Okay, can you guess? I don't know, here. What do you think would be analog of this conjecture? So instead of AD linking diagrams, we would have affine AD linking diagrams. So you would think the conjecture would be that you take tensor product of two affine linking diagrams and you get something which has this property. But actually, so what you need to do is take finite tensor affine. So if you take a tensor product of finite linking diagrams with affine linking diagrams, conjecturally it would have this property. So here's an example. Here's my affine linking diagram. Here's my finite linking diagram. Here's a tensor product. I'm starting. I need to be careful how I orient the arrows. Let's try again. So I basically take a cube. And I will do this. Okay. This is the tensor product of those two thinking diagrams. And so it claims that now if you start running this black, white dynamics here, you will observe if you pick any vertex, kind of just zoom in on one vertex and see what sequence you get there, it will satisfy a linear recurrence. And of course, you don't have to pick those two. You can pick those two and any two where one is affine and one is finite. So what Pasha, the other Pasha, and I can prove is that if you want to have this property, that if you look at each vertex and it satisfies linear recurrence, you must somehow, because there is a new classification similar to this classification, where one of the families is this tensor product. There are other families. There are some exceptional cases. So we can classify all quivers like this, which have a chance of having this property. Now, unlike the Zamolodchikov periodicity, the other direction is not known. So what we don't know how to prove is that if you take any one of those and you start doing the T system, then it will actually, what you see at vertices will satisfy linear recurrences. The only exception is what I drew for you at the beginning over here, when this is affine type A and this is finite type A. So in this case, this looks like a cylinder. Affine type A looks like a circle. Finite type A looks like a line. So quivers here look like a cylinder, kind of. They look like kind of a square grid on a cylinder. So for those, we found some way to prove that it works. That at each vertex, if you look at this vertex and you record the sequence there, it will satisfy linear recurrence. And the proof is very special for this case because it somehow uses this cylinder. It uses the surface. It uses some kind of domino tilings on the surface, whatever. It gives explicit formulas in terms of dominoes or matchings in some graph, etc. So the proof is very special for this case. It doesn't generalize. We don't know how to prove it in general. So if you take something like affine type G here and type A here or anything else here, we don't know how to prove it. So that's an example of something which is widely open. So in fact, I'm not even sure people carefully proved it. I think there may be proof in the literature, but even for just a single affine Dynkin diagram, right? When this guy, this is just one vertex, then the tensor product will be just a single Dynkin diagram, affine Dynkin diagram. The same has to be true. They have to linearize. They have to satisfy linear recurrences. What are the actual formulas for those recurrences? What are the formulas for the coefficients for those conserved quantities? I'm not sure it's written anywhere very explicitly. So if you start, I don't know, with affine type E6 or affine type D, I don't know, you start with quiver, which looks like this. And you start doing this dynamics where you do black, white, black, white, black, white. The claim is that each vertex, whatever sits there, will satisfy a linear recurrence. what is this recurrence? What are its coefficients? Like here, I could give you explicit formula for this coefficient. What are the coefficients of this recurrence? I'm not sure. I don't know where it would be written explicitly. I'm not sure it's written anywhere in the literature. It might be open in some sense. So far, so good. Any questions?
Yes, I wanted to ask, maybe you could provide some motivations for why would we be looking at such T systems, which have the linear recurrence, for example,
Well,
with the
it's a
periodicity.
form of integrability. So
Okay.
people study, so when people study dynamical systems, people study what is called also, I don't know if you met this world, they study integrable systems. And I think originally integrable meant that you somehow can explicitly write a formula for future in terms of the past. Okay, so it means that I think in some in dynamical systems, the division goes like this. A system can be either completely integrable, in which case you can explicitly write solution, or it can be chaotic. So it behaves like chaos, and there is a field of mathematics which studies chaos. Like but then sort of there are various definitions of integrability, and the way we view this linear recurrences as a form of integrability. In fact, it's a rather strong form. There are weaker forms which I can tell you about. But somehow think of it this way: we found just the right form of integrability where the classification would correspond to affine Dynkin diagrams, just like for periodicity, it corresponds to usual Dynkin diagrams, right? So this is a good question because it has a good answer. That's one way to answer. So and I mean there are other, I guess, people have studied things like this, but in much narrower setting. Like I think people have tried to prove similar results in a much narrower setting. So this is a very general setting where we expect this kind of integrability through linear recurrence. So what are some other forms of integrability? The most famous one, which comes from this actual continuous dynamical systems, like when people study like motions of planets around stars or whatever. So the most famous one form of integrability is called Arnold-Liouville integrability. Okay, so I will write it down. So let me write it down. So first, what I told you, linearizability is some strong form of integrability. And by the way, the question about coefficients of those linear relations, that's so people in integral system would call them integrals of motions, the conserved quantities. That's one of the biggest questions in this theory of integrable systems, how to write formulas for integrals of motion. So it very much agrees with kind of what questions people like to ask in this area. So what are some other ones? So another form, the most famous probably form of integrability is called Arnold-Liouville integrability. Arnold. So to prove this form, you need to find something called a Poisson bracket. But maybe let me just say it in a simpler way. So you need to somehow find the right coordinates to write your system so it would look like actual movement on a torus. So the coordinates would come in pairs. You would have integral of motion, something doesn't change, and then something which changes linearly, which you can think of this angle. And then this moves in a circle. And then you have another such pair. You have another integral of motion. But you also have another variable which changes linearly. So this moves on a circle linearly. And product of such circles would be torus. So when people want to prove Arnold-Liouville integrability, it means that they want to somehow change coordinates in your integrable system so that the thing moves on a torus, rather like linearly moves on a torus with constant speed. So, but it's like it's a whole science. You like it's impossible to describe. Like it's a whole area of mathematics. So, but one conjecture would be that everything which is integrable in this sense is also integrable in this sense. So one of the open questions which we didn't solve, but which we strongly believe is that all our systems which satisfy linearizability, you could correctly put them in the setting of this Arnold-Liouville integrability. So, which is another, I guess, confirmation that this is somehow a good definition, that it's just a stronger form of this, which gives you the right answers. It gives you the right answer of affine Dynkin diagrams. There's another form in integrability which people which study discrete systems like. So, right, so Arnold-Liouville stuff is actually more suited for continuous system. You can apply to discrete systems like this, but it's more suited for continuous systems. So the thing which is suited for more algebraic and discrete systems is called zero algebraic entropy. And roughly speaking, it just means that if you keep applying your algebraic map, the degree should not grow too fast. It should grow at most as exponential of a polynomial. Okay, so that's the definition. And you could ask, well, which of the T systems of the kind we are looking at would have zero algebraic entropy? And it turns out that also fits in that's also the right question from our point of view. And the answer to this question is that those are affine product affine pures. So somehow there are three stages of being integrable in this world. If you take bipartite T systems, if you are finite times finite quiver, you are just periodic. That's what Zamolodchikov noticed. If you are fine times finite, you will have this linearizability property. And if you are affine times affine, does everybody understand what affine times? It's just like an example would be just tensor product. So you have a affine Dynkin diagram, you have another affine Dynkin diagram, and then you take the tensor product, whatever that's supposed to be over here. So if you take two types A, that will be like circle times a circle, which is a torus. So those will look like square grid quivers on a torus. So those are the ones which we can prove are the only ones which could have zero algebraic entropy. But again, the other direction we don't know. There's a huge number of those guys, and we cannot prove that they actually have zero algebraic entropy. We can confirm it, but by our calculations, but we cannot prove it like possibly even for type A times type A. We cannot even prove it for that case. So that's somehow hierarchy of integrabilities here. Anyway, so any other question? I don't know. We are kind of running out of time. I'm not sure I will have time to tell you about. I'll tell you something about Volkov's proof, but not sure how much detail I will be able to tell you. So I will try to email to you. I will email to you those couple papers I have with Zaza Pasha where we state those conjectures. I think they're interesting. They're very much open and they're delicate. I don't know. Anyway, if you like them, you can try to talk to me about them. Maybe you can help us to figure out how to do them. But any other questions? I can try to say something else about all of this.
Is there any notation where you can find more information about these integrability systems and multiplication of affine and affine diagrams?
So this would live in our work with Pasha. So the best thing for this is the papers I wrote with Pasha, which I will send to you. Integrability, there is vast literature on Arnold Liouville integrability. The most famous book about it is this classical book by this Soviet mathematician Arnold. Where is it? It's called Mathematical Methods of Classical Mechanics. So for this you find this book by Arnold called Mathematical Methods of Classical Mechanics. It's a very famous book. It's very well written. It's very educational, but it's like a whole area. So I can try to find for you other things to read about it, but it's a beautiful area. So again, you know, I'm a discrete person. I do combinatorics, I do algebra. I kind of learned a little bit about integrable system kind of late in my life. But it's a very beautiful area. It's interesting because somehow the same stuff, the same ideas people apply to motions of planets around, you know, sun or whatever, people apply to studying systems like this. So it's kind of, for me, it was very interesting. I kind of regretted not learning more about it when I was young. So I'll try to find something besides this book and send to you guys. So if you're interested in this area. So algebraic entropy is a kind of a young concept. It applies only to kind of algebraic maps, right? It's something you can say about taking an algebraic map and applying it again and again and again to itself, kind of many times. So it's a much smaller thing. There's not so much literature about it. I can try to send you something about it. But overall, I think somehow, so maybe the lesson here is that integrable systems have actually been one of the main areas where cluster algebras found their applications, because I mean for various reasons, but somehow many of the maps produced by cluster algebras turn out to be integrable, and the other way around. Many of the maps people knew to be integrable, it turns out you can write them in terms of cluster algebras. And those Zamolodchikov ones, the periodicity, you can think of periodicity as extreme integrability. If you are periodic, you are extremely integrable. Everything is a conserved quantity. Everything comes back to where it started. So that's it. So I'll try to find something interesting for you to read about this. And any other questions?
So about the linear.
A bit louder.
So you said that periodicity is kind of extreme integrability. So are periodic sequences generated by linear recurrences also, or no?
Yeah, you could say so. So it's kind of silly. I mean, yeah, the answer is yes. So imagine that you have a periodic sequence. A1, A2, AN, and then you have AN plus 1, which is equal to A1, etc. This satisfies linear recurrence AN plus 1 equals to I equal to AI. This is a linear recurrence. It's a very special kind of linear recurrence. So those three things kind of sit inside each other. So there are things which have zero algebraic entropy. inside them, there are things which are linearizable. And inside them, there are things which are periodic. And if you're periodic, you can be viewed as being linearizable because you satisfy very silly linear recurrence. Yeah.
Yeah, I see. Thank you.
And similarly, you can prove that if you're linearizable, you have zero algebraic entropy. So it's a hierarchy, and it's kind of so those are finite times finite Dynkin diagrams. Those are finite times affine, and those are affine times affine. But again, we fully understand only this one. Only in this case, we can prove if and only if statement. For those two, we can prove that if it has those properties, it must be of this finite times affine or affine times affine kind. But we cannot prove the other way around. We cannot prove that those actually work. We can try small examples and observe that they work, but basically there is a huge classification and many families, and not for a single one we can prove that it works. Okay, let me tell you something about, I don't know, I have like 5 minutes to tell you something about Volkov's proof, which is unfortunate. Yeah, you probably will have to skip it. But the idea of Volkov's proof is roughly like this. So let me remind you. So what we are trying to prove? We are trying to take a tensor A case, which looks like this. And we are trying to prove that in this case, the system is periodic. So here was the Volkov's idea. He said, let's take something called Grassmannian. I don't know if you guys would know what is Grassmannian. So strictly speaking, it's not a super complicated, it's just, strictly speaking, it's a variety of k-dimensional subspaces in an n-dimensional space. Which, like, in simple terms, you can just think of it as every point in it is just k by n matrix. And this variety has so-called Pluka coordinates. So if you think about it this way. You have k vectors of length n. That's what those rows are. K vectors of length n. They will define for you some k-dimensional subspace of n-dimensional space. But you're allowed to do something with them. Like if you add this row to this row, it will change this matrix, but it will not change the subspace. It will still be the same subspace. So you kind of think of it as you mod out by action of SLK on the left, meaning that you're allowed to do any row operations. You're allowed to do any row operations, and you still have the same point in the Grassmannian. And then you could ask, well, how can we measure anything on this? Like this entry over here, it doesn't really exist. It's not a function of our subspace, right? We can write our subspace, so this number will be one thing, but then we can do some row operation and this number will change. So this number is not a well-defined function on this variety. But if you take a determinant of size k, basically if you pick some k columns, and you take this determinant with those columns, it's called maximal minor, right? So if you take this maximal minor of this matrix, the determinant will not change because roughly speaking, when you multiply by something in SLK on the left, you multiply this determinant by 1, so it doesn't change. So people talk about Pluka coordinates, which correspond to k by k determinants inside this k by n matrix. So basically, Zamolodchikov idea was he came up with a kind of a tricky way to choose specific determinants from here and plant them over here. Here, I'll show you how you could start, for example. So if this is like 4×8 matrix, okay, let's take 4×8 matrix, then you would start with something like, let's see, 2, 3, 4, 8, 2, 3, 7, 8, 1, 3, 7, 8. So each of those is just a set of columns, right? So, okay, you cannot see very well. I don't know, can you see like this? Sort of.
Yes, we can.
Yeah, so for each vertex, you write a subset of k columns from n choices, right? So here you would write 2, 3, 4, 7, 3, 4, 7, 8, and maybe 3, 6, 7, 8. And there's some rule how to do it, which I was going to tell you, but I don't have time. 3, 4, 5, 7, 3, 4, 6, 7. And the last one is 4, 6, 7, 8. 4, 6, 7, 8. So you could start, for example, with those, but the point is that now if you start applying our recurrence, the new values will also be those 4×4 determinants. So you will be replacing, there are some relations they satisfy, and you will be replacing some determinants here by some other determinants. And then you kind of see that this whole thing kind of cyclically shifts until it comes back to where it started. So, and that's how you observe that eventually things come back where you started. So you just say that whatever numbers you put here, you just find correct subspace, which will give you those numbers as those determinants. And then you know that on the next time iteration, you will have some other determinants, and the next time will be other determinants. But the way they change, you can tell that it's periodic because it somehow just cycles through those columns of this matrix. Okay, so it's a vague idea. Sadly, I don't have time to tell you more, but very vaguely, this was his proof. I will attach the paper, which you will not recognize this in his paper because it was written in a very different language, but I will try to show you his paper. I mean, his argument is very, very beautiful. But there is something very special because this only works for this kind of grid thing where it's type A times type A. It's just there's nothing like Grassmannian which would give you something like this for other products, like A times G or something like that. Okay, I think I ran out of the things and time more importantly. So I don't know. I hope you enjoyed this, guys. I mean, I will try to send you something interesting to read. Any more questions I can answer for you?
I have a question. You mentioned 3 forms of integrability before that, right?
That's right.
Are there any other forms? So just we are done with those.
There are other forms. So I don't know how to. So again, the main form for most people, when they talk about integrability, they probably will mean Arnold-Liouville integrability. The other ones are more rare. However, there is many other forms. And they are all interesting and they are all kind of magical. In fact, there is no, like if somebody tells you that a system is integrable, it's almost like they're telling you that it's magical. It's very imprecise. It just says there's something magically working out nicely for the system, but depending on your definition, it could be very different things. So the 3 I told you about are the most interesting from a point of view of a discrete person. Right, so I told you about linearizability, I told you about algebraic entropy, I told you about Arnold-Liouville one. I'll have to try to remember. I think the Japanese school has their own kind of version of integrability, which I kind of forgot how to describe. But yeah, I think there may be other ones too. Yeah, you can define it in many ways. But again, so original understanding of this word integrable goes to the following problem. Somebody just writes for you dynamical system. It can be continuous, it could be like differential equation, or it can be discrete, something like a recurrence we just saw. And then you need to write down what it will be in the future at time t. And for some systems, it's impossible. Some systems behave so chaotically that it's just impossible to write down any formula or anything at all about. And such systems are studied by chaos. Like there's area of mathematics called chaos. And it's much closer to analysis. But for some systems, which are very rare, you can write formula. They just happen to be nice enough that you can write formula for future in terms of the present, explicit formula. And such system people traditionally called integrable. So that's what sort of it's where it originally comes from. So it even precedes this Arnoldi-Will one. It's just is your system predictable? And this kind of system is much closer to algebra. So if like so chaos is a part of analysis. Integrable systems is part of algebra. And so I guess what else? By the way, interesting question is like real life systems. Which way are they? Like moon orbiting Earth. Is it integrable or is it not integrable? So I actually asked at some point my colleagues who study this kind of thing. So the answer is actually surprising. So almost any system in nature will not be integrable, but will be close to integrable. So it's kind of a surprising answer. It's so to find something perfectly integrable is extremely unlikely. You almost never find it. But yet somehow those systems are not completely chaotic either. There's a way in people kind of figured out that they're close to being integrable. So I don't know. That's as much as I understand about this. But anyway, I'm a discrete and / algebraic person, so I'm not the right person to ask about like moon or whatever. But I'll try to send you something interesting to read about those kinds of integrability I mentioned to you.
Thank you.
Yeah, it's a beautiful area. I mean, and as I said, I wish I wish I knew about it sooner. I wish I knew about it when I was student, and like I wish somebody taught more me about it when I kind of had to catch up when I was not student anymore. Okay, really nice seeing you guys. Thank you for coming. I hope this was useful. I mean, it's a bit overwhelming world, and I mean it was a bit fast how I went through it, but I'll try to send you papers, and feel free to email me and ask questions. And if you feel like trying to figure something out, you can try and you can talk to me about it, etc. Otherwise, enjoy your next mathematical adventure. Hopefully I'll see you more. Nice seeing you guys. Glory to Ukraine. Hope everything will be okay.